So today we're going to be doing May-June 2023, paper 51. Question number 1 says, the partition coefficient shows the distribution of a solute between two immiscible solvents. The partition coefficient KPC is determined by measuring the concentration of the solute in each solvent. The organic solvent ethoxyethane and water are immiscible. A student is asked to find the partition coefficient of butane dioic acid between ethoxyethane and water. So this is our objective. We want to find the partition coefficient of butane dioic acid, and our two solvents are ethoxyethane and water. The expression for KPC when butane dioic acid is in equilibrium between ethoxyethane and water is shown. They've also given us the density of ethoxyethane and that of water. The student uses the following method to find the partition coefficient. A diagram of the apparatus is shown in figure 1.1. So in step 1, you add 30 cm³ of distilled water to a separating funnel. Weigh by difference 2.81 grams of butane dioic acid into the separating funnel. Again, weigh by differences, we first measure the mass of the solid and the container, and then we transfer the solid and we reweigh, right? And we take the difference to find the mass of solid that was transferred. We stopper the separating funnel and shake it until the butane dioic acid has dissolved. Remove the stopper and add 30 cm³ of ethoxyethane to the separating funnel. Okay, so initially we have distilled water. We dissolve the butane dioic acid. Okay, we dissolve the butane dioic acid in water, right? We dissolve it in water in the separating funnel, and then we add 30 cm³ of the organic solvent, that is ethoxyethane, to the separating funnel. We replace the stopper and shake the separating funnel gently. We place the separating funnel into a clamp, allow the liquids to settle so that the two layers can be seen. Okay, so now what's happening is that the butane dioic acid, which is your solute, is separating into the two different layers. Your two different layers are ethoxyethane and water, right? So the solute is distributing itself between the two different solvents. Then we remove the stopper and open the separating funnel tab to allow the lower layer to run into a beaker labeled A, and we run the upper layer into a beaker labeled B. Then we transfer 10 cm³ of the aqueous layer into a conical flask, and we titrate with 0.5 mole per dm³ aqueous sodium hydroxide using thymophthalene as an indicator. Lastly, we take 10 cm³ of the ethoxyethane layer and add 10 cm³ of water to it. We titrate this mixture with 0.1 mole per dm³ sodium hydroxide aqueous. Okay, so now we're using 0.1 mole per dm³ instead of 0.5 mole per dm³ sodium hydroxide. And again, we're using thymophthalene as an indicator. So here's the experimental setup, right, for the separation. We first add the water, which is the lower layer, right, because water is more dense. Okay, water is more dense. So the lower layer is the aqueous layer, right, and then the organic solvent will be the upper layer, right, because it's less dense than water. Okay, we mix the contents of the flask, and then what we do is we remove the aqueous layer. We open the tap and we remove the aqueous layer into a beaker, and then we run the ethoxyethane layer into a separate beaker. Okay, and then we do a titration. Now state whether beaker A in step 7 contains the aqueous layer or the ethoxyethane layer. Now the beaker labeled A contains the lower layer. The lower layer is the aqueous layer. Okay, the lower layer is the aqueous layer. And the reason the lower layer is the aqueous layer is because water is more dense, okay, than ethoxyethane. Water is more dense than ethoxyethane. Identify the piece of apparatus that should be used in step 8 to transfer 10 cm³ of the aqueous layer. You should use a 10 cm³ volumetric pipette, okay, a 10 cm³ volumetric pipette. Okay, again, you can just say pipette, but a volumetric pipette is the pipette with a single graduation mark, right, for the 10 cm³. So again, the pipette will measure specifically just 10 cm³, right? It won't be able to measure any other volume. Suggest why water is added to the ethoxyethane layer in step 9 before the titration can take place. So let's go to step 9. right? Now what we're doing here is we're 10 cm cube of the ethoxyethane layer, and then we're adding 10 cm cube of water and then titrating the mixture. Now our objective is to find the amount of solute present in the ethoxyethane layer, right? Our objective is to find the amount of butane dioic acid, that's the solute in the ethoxyethane layer. But the reason we're adding water is because in order for sodium hydroxide to react, okay, in order for the sodium hydroxide to react with the butane dioic acid, right? We have butane dioic acid. In order for the sodium hydroxide to react with the butane dioic acid, the butane dioic acid has to be in its aqueous form. Okay, it has to be in an aqueous form, right? The reason why we're adding water is because we have aqueous sodium hydroxide, and since the sodium hydroxide dissolved in water, it won't mix with the ethoxyethane. So you won't be able to react the sodium hydroxide with butane dioic acid. Why? Because the butane dioic acid is in the ethoxyethane, and the water and the ethoxyethane are immiscible. So in order to get a reaction, we add the water to it. The butane dioic acid will move from the ethoxyethane to the water, and then the sodium hydroxide will be able to react with the butane dioic acid in the water. Okay, so the reason we're adding water is so that the butane dioic acid in the organic layer moves into the water so that it reacts with the sodium hydroxide. The butane dioic acid, okay, butane dioic acid, okay, moves from the ethoxyethane, okay, ethoxyethane into the water, okay, and then reacts with the sodium hydroxide. Okay, for a 2.81 gram sample of butane dioic acid, the titer for the aqueous layer is 27.25 cm cube, and the titer for the ethoxyethane layer is 22.5 cm cube. The equation for the reaction between butane dioic acid and sodium hydroxide is shown. Calculate the concentration of butane dioic acid in the aqueous layer. Now for the titration of the aqueous layer, right, we took 10 cm cube of the aqueous layer. Okay, we took 10 cm cube of the aqueous layer and we titrated it with 0.5 mole per dm cube sodium hydroxide. Okay, so over here the concentration of sodium hydroxide is 0.5 mole per dm cube. The volume of sodium hydroxide used is 27.25 cm cube, right? That's the volume of the titer for the aqueous layer. And then the volume of the aqueous layer itself, the volume of the aqueous layer itself is 10 cm cube. Okay. Now the first thing we can do is we can find the number of moles of sodium hydroxide. So the number of moles of sodium hydroxide is equal to the concentration times the volume. This is equal to 0.5 times 27.25 divided by 1000. This gives us 0.013625 moles of sodium hydroxide. Okay, so we have the moles of sodium hydroxide 0.013625. That means that the number of moles of butane dioic acid, okay, butane dioic acid is the number of moles of sodium hydroxide divided by 2, right? Because we have a 1 to 2 ratio. 2 moles of sodium hydroxide reacts with 1 mole of acid. That gives us the number of moles of acid as 0.0068125 moles. And now we want to find the concentration of the acid. We want to find the concentration of the acid in the aqueous layer, right? And that is equal to the number of moles divided by volume. Number of moles is 0.0068125 and the volume is 10 cm cube. The volume of the aqueous layer is 10 cm cube, which is 10 divided by 1000, which is 0.01 decimeter cube, right? We have to convert from cm cube to dm cube. So that would be 10 divided by 1000, that's 0.01. And that gives us the concentration as 0.68125 moles per decimeter cube. Okay. Calculate the partition coefficient KPC. Now the partition coefficient is the concentration of acid in the organic layer divided by the concentration of acid in the aqueous layer, right? We found the concentration in the aqueous layer, now we need to find the concentration in the organic layer. Now going back, we see that we used 10 cm cube of the organic layer, right? We used 10 cm cube of the organic layer. And in this case, we use 0.1 mole per dm cube sodium hydroxide. Okay, so we're not using the same sodium hydroxide as we did for the aqueous layer. We use 0.1 mole per dm cube sodium hydroxide. Okay, and then the volume of sodium hydroxide used, okay, the volume of sodium hydroxide used is 22.5 cm cube, right, for the ethoxyethane layer. So over here we can say that for the organic layer, right, for the organic layer, we talk about the titration, right? The number of moles of sodium hydroxide, is the concentration times the volume. The concentration was 0.1 mole per dm cube this time, and the volume is 22.5 centimeter cube. Okay, the volume is 22.5 centimeter cube. 0.1 times 22.5 divided by 1000, and that gives us 0.00225 moles. Okay, 0.00225 moles, which of course again means that the number of moles of acid is the number of moles of sodium hydroxide divided by 2, again because they're reacting in a 1:2 ratio. So that is 0.001125 moles. So now we have the number of moles of acid in the organic layer, right? The number of moles of acid in the organic layer, and we know that the volume of the organic layer was 10 centimeter cube, which means that the concentration of acid, okay, the concentration of acid in the organic layer is number of moles divided by volume, which is 0.001125, divided by the volume, which is 0.01 decimeter cube. Again, that's 10 cm cube divided by 1000. So that gives us the concentration as 0.1125 moles per decimeter cube. And now we have to find the partition coefficient. That's the concentration of the acid in the organic layer. That's your solute, 0.1125, right? Divided by the concentration of the solute, right? The acid in the aqueous layer, that was 0.68125. 0.68125. And that gives us the answer as 0.165. Okay, 0.165. Partition coefficients are unitless, right? It doesn't matter what units you use, okay? It doesn't matter what units you use for the concentration as long as the units in the numerator and the denominator are the same. B part 3 says explain why the student is only able to repeat the titration in step 8 once. Now if you wanted to repeat the titration, you're going to need another 10 cm cube of the aqueous and the organic layer, right, for the titration. You're going to need another 10 cm cube for the aqueous and the organic layers. Now if we go back, right, we see that we only prepared 30 cm cube of each. We only prepared 30 cm cube of each. Now we used up 10 in the first titration of each. We used up 10 cm cube in the first titration of each layer. If we take another 10, then we've used up 20, right? So theoretically we have 10 left, but there's no way to transfer the entire 10 that's left over the third time, right? So you take 10, okay, you take another 10, that's 20, that's 2 titrations. And if you take a third time, right, you won't be able to get exactly 10 because there's always going to be some of the layers left behind. There's always going to be some of this 30 cm cube left behind. You can't pipette from a container such that the container is completely empty. Okay, you can't pipette from a container such that the container is completely empty. So there'll always be something left behind. Okay, there'll always be something left behind. So if you wanted to do 3 titrations, you want to make more than 30. You want to make something like 35 or 40 cm cube. Okay, so the answer here is that it is not possible. Okay, it is not possible, okay, to pipette all of the aqueous or organic layers. Okay, some will always be left behind. Okay, some will always be left behind when you're pipetting. Okay, suggest how you would modify the procedure to ensure that the student can repeat the titration in step 8 more than once. You would just use a larger volume. Okay, you would use a larger volume than 30 cm cube. Okay, than 30 cm cube. of ethoxyethane and water. Okay, ethoxyethane and water. A different student forgets to shake the separating funnel in step 5. Describe the effect this would have on the calculated partition coefficient value. Explain your answer. Now, initially what we had done was we had dissolved the butane dioic acid. Okay, we had dissolved the butane dioic acid in water. Okay, so initially we had added distilled water, and then we had dissolved the butane dioic acid in water, right? We had dissolved it in water, and then we added the ethoxyethane, and then after that we shake the separating funnel, right? Now, if you don't shake the funnel, that means that not all the butane dioic acid that's supposed to move into the ethoxyethane layer moves into the ethoxyethane layer, right? Because for the partition coefficient, equilibrium has to be attained. The reason we're shaking the separating funnel, is to ensure that equilibrium has been achieved. Okay, if you don't shake the separating funnel, it'll take longer to get to equilibrium. That means that some of the butane dioic acid will remain in the water that was supposed to go to the ethoxyethane. Okay, in other words, there will be more butane dioic acid in water. So there will be more butane dioic acid in water, which means that your partition coefficient will be smaller. Okay, because the concentration in water will be greater and the concentration in the organic layer will be lower. Okay, the concentration in the organic layer will be lower. And we know that for the partition coefficient, the organic layer is in the numerator, water is in the denominator, right? So we would say the effect on KPC is that the KPC would be lower, okay, would be lower. And the reason why is because equilibrium has not been attained, okay, has not been attained, okay. Therefore, there is a greater amount, okay, there is a greater amount of the butane dioic acid in the aqueous layer, okay, in the aqueous layer. So here we have question number 2, which says paper chromatography can be used to separate the individual amino acids formed when tripeptides are hydrolyzed. One molecule of a tripeptide produces 3 amino acid molecules when hydrolyzed. A student is asked to identify the amino acid formed from the hydrolysis of 3 different tripeptides A, B, and C using paper chromatography. Figure 2.1 shows the results of the student's chromatography experiment. Okay, so we have the results of the chromatography experiment shown here. The individual amino acids can be identified from their RF values. Suggest why each sample is applied to the chromatography paper using a thin capillary tube rather than a dropping pipette. Now, the reason we use a capillary tube is because we just want to apply one small drop, okay, or one spot of the sample, right, for each of the samples A, B, and C. Okay, if we use a dropping pipette, okay, it's not as controlled. We can accidentally add more than we need. So the reason we use a capillary tube is to add the sample in a more controlled way. Okay, to add the sample in a controlled way, right? Basically, you're saying that to ensure that just a drop of the sample is added. Okay, to ensure that just a drop of the sample is added. Suggest why it is necessary to spray a developing agent over the chromatography paper before the chromatogram can be analyzed. So a developing agent is also known as a locating agent. Okay, a locating agent is used when we have colorless drops, okay, or we have colorless samples, right? The locating agent helps us identify the spots, okay, or it makes the spots visible. Okay, so a locating agent simply makes the spots visible. Okay, makes the spots visible. Okay. Table 2.1 shows RF values for some amino acids in the solvent used in figure 2.1. Use the data in table 2.1 to identify the amino acids in tripeptide A. And we go up to tripeptide A. So they've given us the RF values. So what we need to do is we need to find the RF values for each of these 3 spots. So here you should draw the line from the center of the drop to the ruler. The distance traveled is roughly 1.05, okay, for A1. I'm going to call this spot A1. Okay, so for A1, the RF value is the distance traveled, that's 1.05 divided by 7. Okay, so we get 1.05 divided by 7, which is 0.15. Okay, for A2, that's the second drop, the distance traveled is roughly 3.75. Okay, the distance traveled is roughly 3.75 divided by 7. So the RF value, 3.75 divided by 7. So the RF value here is 0.5357. So that's 0.54. And then for A3, the RF value is around 5.5 divided by 7. Okay, and it's the distance traveled by the sample divided by the distance traveled by the solvent front. So we get 5.5 divided by 7. So the answer is 0.79. 0.79. Okay, so our RF values are 0.15, 0.54, and 0.79. Okay, 0.15, 0.54, and 0.79. So those correspond to lysine, 0.15 roughly. Okay, 0.54 is closest to tryptophan. Okay, it's closest to tryptophan, and then 0.79 is closest to leucine. Okay, it's closest to leucine. Even though those values are way off, okay, even though those values are way off from these, okay, we have to look at which of these are those RF values closest to. Okay, so the answer here is lysine, tryptophan, and then leucine. Suggest why the hydrolyzed sample of B produces only 2 spots. The reason it produces only 2 spots is because we have a tripeptide, but we could have 2 identical amino acids, right? A tripeptide is made of 3 amino acids, but it doesn't have to be 3 different amino acids. You could have 1 amino acid of one type and then 2 amino acids that are the same. You could have 2 identical amino acids and then a third amino acid, right? So what we have here is the reason we get only 2 spots is because there could be 2 identical amino acids present, okay? Or 2 of the amino acids, okay? 2 of the 3 amino acids are identical, okay? Two of the spots from the hydrolyzed sample of C overlap. State the reason for the overlap. Now, in the sample of C, we see that these 2 spots are overlapping, which means these 2 amino acids must be similar, okay? They must be similar. In other words, they probably have similar solubility in the solvent, right? For example, because we know that as the solvent moves up, it carries the amino acids with it, right? Whichever amino acid is more soluble will move a greater distance, right? Whichever amino acid is more soluble will move a greater distance, right? Because the solvent is the mobile phase. So these 2 amino acids could have similar solubilities, which means that they're similar amino acids, and therefore they have similar RF values. Okay. So here we can say that the 2 amino acids, okay, have similar RF values. Okay, but that's not really a good reason. Okay, the reason why is because they have similar solubilities. Okay, they have similar solubilities in the solvent. Okay, similar solubilities in the solvent, or you can say that they have a similar affinity towards the chromatography paper, right? Suggest an improvement to the method that would allow the overlapping spots to be distinguished clearly. Now again, because you have similar solubilities in the solvent, right, you could use a different solvent. Okay, you could use a different solvent. Okay, use a different solvent, right, so that their solubilities are not similar in that new solvent. Okay, or what you could also use is a longer paper, right? If you use a longer paper, okay, if you use a longer paper, you allow more time for separation. If you use a longer paper, you allow more time for separation, so it'll be easier to distinguish between these two. Okay, So you can also use a longer chromatography paper. So here we have question number 3, which says a scientist is asked to find the rate of decomposition of an aromatic diazonium compound and determine the order of the reaction with respect to the aromatic diazonium compound. Part A says the scientist is given 1.02 grams of an aromatic diazonium compound in a 50 cm3 beaker. Describe the steps the scientist should take to make a 100 cm3 standard solution containing 1.02 grams of this compound. Give the name and capacity of the apparatus the scientist should use. Write your answer using a series of numbered steps. Now again, we want to prepare a solution from a solid. Okay, the 1.02 grams is given in the beaker. So what we're going to do is we're first going to add a small amount of distilled water. Okay, add a small amount of distilled water to the beaker. And stir to completely dissolve. Okay, and stir to completely dissolve the solid. Okay, dissolve the solid. The next step is to transfer. Okay, to transfer the solution to a 100 cm3 volumetric flask. A 100 cm3 volumetric flask. Okay, I'm going to mention in parentheses that for this we're going to use a funnel, right? And then what we're going to do is we're going to rinse the beaker. We're going to rinse the beaker. And I'll mention again in parentheses that we should also rinse the glass rod and the funnel, right, with distilled water. Okay, but they don't usually ask for that detail, but I'm still mentioning it. With distilled water, and transfer the washings. Okay, and transfer the washings, right, to the 100 cm3 volumetric flask. And then lastly, we're going to make up to the mark. Okay, make up to the mark with distilled water. And again, I mentioned this previously that they didn't really ask for this often, but in recent papers they have asked for this. Okay, so make up to the mark with distilled water and then invert the flask, right? Invert the flask to mix the solution. Okay. Benzene diazonium chloride, an aromatic diazonium compound, decomposes in solution to produce phenol and nitrogen gas. The scientist warms 50 cm3 of the solution to 50 degrees Celsius. The scientist records the volume of nitrogen gas produced at different times during the decomposition. Identify the piece of apparatus that should be used to maintain the temperature of the solution. We're going to use a thermostatically controlled water bath. Okay, a thermostatically controlled water bath to maintain the temperature. Identify the dependent variable. Here we're setting the temperature to 50 degrees Celsius and the volume of gas produced at different times is the dependent variable, right? Dependent variable is the volume of the nitrogen gas. Okay, the volume of the nitrogen gas. Suggest why the scientist does not monitor the reaction by measuring the loss in mass. Because we have a loss of gas over here, right, we know that the mass of the contents will decrease with time. So we could study the rate by looking at the loss in mass with respect to time. However, because our entire apparatus is inside a water bath, right, that's thermostatically controlled, we can't really measure the mass. Okay, so over here we would say that it is not possible, okay, not possible to monitor, okay, not possible to monitor the weight, okay, the weight of the apparatus. Okay, because of the use of the water bath. Okay, table 3.1 shows the results of the experiment. V final is the final volume of nitrogen gas measured once the decomposition is complete. Vt is the volume collected at time t. V final minus Vt is proportional to the concentration of the benzene diazonium chloride. Okay, now this is a key statement. V final minus Vt is proportional to the concentration of the benzene diazonium chloride. Complete table 3.1. They haven't mentioned the decimal places or the significant figures, but based on what we can see here, right, we should write down all of these volumes to one decimal place, right? They've shown that here clearly, right, with this value here. So all the volumes, all the V final minus Vt should be written to one decimal place. Plot a graph on the grid in figure 3.1 to show the relationship between V final minus Vt and time. Use a cross to plot each data point. And draw a curved line of best fit through the plotted points. Okay, so here's my line of best fit. Okay, here's the line of best fit that I've drawn. Okay, we can see that we have this anomalous point here. Okay, I'm going to circle this anomalous point. Going back up, question says circle the one point on the graph that you consider to be the most anomalous. We just did that. Suggest one reason to explain the anomalous point. Assume no error was made in the measurement of the volume. Okay, assume no error was made in the measurement of the volume. And what that means is that there is no error made in this measurement here. Okay, there is no error made in this calculation here because we haven't made any errors in measuring the volume, because we haven't made any errors here, okay, or here. There's no errors made in the volume. Okay, no errors made in the volume. So that means that the error was made in recording the time. Okay, the error was made in recording the time. Now for this particular V final minus Vt, for this particular V final minus Vt, right, this point should be further to the left. This point should be further to the left, right? So the time taken should be lower. The time taken for this particular point should be lower. So that means that the actual time taken was lower. The actual time taken was lower, whereas the recorded value, the value we recorded, right, we got a greater value of time than the actual amount, right? Again, because the volumes are measured accurately, this particular volume corresponds to a lower time. So the actual time that had elapsed was lower, and the recorded time, the one that was recorded in the table, is higher than the actual time. So what we did here was we actually made the measurement of the volume earlier. Okay, the volume itself was measured earlier, right? So the answer here is that the volume, okay, was recorded at an earlier time. Okay, at a time earlier than the recorded value. Okay, than the recorded value. Okay, again, this is another way of saying that the actual time, okay, the actual time at which the volume was taken, okay, the actual time at which the volume was taken, okay, at which the volume was recorded, the actual time at which the volume was recorded, okay, was before the recorded time. Okay, it was before the recorded time. So that's the reason for the anomaly. Use your graph to find two successive half-lives for this reaction. State the coordinates of both points you used in each of your calculations. Now going back to the graph, right, for the first half-life here, okay, for the first half-life here, we've gone from 57.2 to roughly 28.6, okay, 57.2 to 28.6, okay, so the y coordinate is roughly 28.6 and the x coordinate is roughly 9.5, okay, 9.5, right, that's the time taken, and the y coordinate is roughly 28.6, okay. So for the first t half coordinates, we used 0 and 57.2, right? That was the initial point, right? At t is equal to 0, 0 and 57.2, and then 9.5 and 28.6. Okay. 9.5 and 28.6. So the first half-life comes out to roughly 9.5 minutes, right? That's the x coordinate, 0 to 9.5. Now for the second half-life, I started from here 9.5 and 28.6, and then I ended at roughly 19.25, and this is roughly 14.5, okay, or 14.3, Okay, that's what we were trying to approximate, right? The half of 28.6 is 14.3. Okay, so roughly 14.3. So we have 19.25 and 14.3. So what do we have? The second point is 19.25 and 14.3, and the first point is the same as this one. That's 9.5 and 28.6. So the half-life again is the difference in the time values. So the half-life comes out to 9.75 minutes. Right, so what we see is that the first and the second half-lives are roughly the same. Use your answer to C part 5 to state the order of the reaction with respect to the benzene diazonium chloride and explain your answer. So it's order 1 because the half-lives are constant. Okay, half-lives are constant. Okay. I've taken successive half-lives, but you don't have to take successive half-lives. Okay, so that's the answer.